Okay, we finished by by some statement about the relation of the Calogero-Moser system and the KP equation. And I would like to recall some statements. So first of all, an equation. The equation, the KP equation. So I use it in the following form. It is written for the function u on three variables, x, y, and t. And it is the following partial derivative equation over dx d over dt 1 over 4 6u du over dx plus the third derivative of u with respect to x. Okay. And as I remember, one of the home tasks was to demonstrate that this equation is equivalent to the following condition: d over dy minus L1 d over dt minus L2 is equal 0. There L1 and L2 I will write the derivation with respect to x with the simple with the sign d, because it's a particular variable plus u, and L2 is d3 over dx3 2u over dx plus w. Okay. And another object was the Calogero-Moser system. Calogero-Moser system is the system of ordinary equation. So it is written on variables x, y, which are position of some particles on the line. And it is written in the following form: over xi minus xj power 3, and with some overall all j which are not equal to I. And this system is Hamiltonian with the following Hamiltonian: to some pi nu I square. Okay, I will use the following normalization: xi j minus 2 with the canonical bracket between momenta and positions of particles, and it has Lax representation. I will use it in the following form: L ij is x pi delta ij plus 1 over minus xj 1 delta ij. And so the Lax representation here means that this equation is equivalent to the equation some lambda no, it's L. So L dot is equal to ML, and I need M, which is minus delta ij sum jxi j square plus 1 minus delta ij xi minus xj square. You understand approximately what is the metric structure of these matrices. So L is a matrix which is of this type P1, Pn, as for the Lux operator of the Tode chain, and here we have on the th and jth place we have 1 over xi minus xj. Okay. And M is a little bit different, so at the generic point, a generic place with I not equal to j, it has the value xi minus xj square, and this means that the sum of mij over j is 0. Okay, so it is normalized in such a manner that the sum of all entries in one row is 0. Okay, but you see, it's a Lux representation of the different system, not of the Tode chain, but it has some similar properties. So it's a statement, it can be verified, and it was the home task. So there is a relation between these objects, and they are due to this representation. So you see, this operator, it's a Sturm-Liouville operator with some potential. Schrödinger, non-stationary Schrödinger operator, and it was observed that it is important to understand this operator separately. So this condition, which is equivalent to this equation, is a condition of consistency of two linear problems. I will erase this. I hope you remember it. So I will need only the form of this Lux representation for this system. So it was a revolutionary idea to understand this condition concerning the corresponding linear problems. Over L psi L0 and d over dt minus L1 and L2 psi equals 0. So you see the system of linear equations on y and t and on psi has a common solution, or it is most likely that it has a big space of common solutions if and only if these operators are consistent. Have you discussed the curvature, notion of the curvature on a manifold along the course of differential geometry? Yes? So we can understand this equation as a connection on a two-dimensional variety. So this is variety of t and y, and this operator is defines some connection in some bundle. It is infinite dimensional, but infinite dimensional. Yes, it is infinite dimensional because it's a differential operator on x. But principally, it is the same construction as a connection on some vector bundle, but in infinite dimensional. And the consistency condition, which is the condition of the zero curvature of this connection, means that you have some trivialization, some flat horizontal trivialization of the bundle. You understand? So, but it means that you can find just a basis of section of this bundle, which are horizontal, and it means that they satisfy both equations. And the effect of completeness of this family of solutions means that it is zero curvature. So this interpretation of this nonlinear partial derivative equation in terms of the consistency of two linear problems was crucial in inverse scattering method in field theoretical integrable systems. So we will discuss it on an example of this equation. So we will try to understand what is this linear problem. And okay, I will formulate a theorem, and we will prove some part of this strong theorem. So it is the theorem of of my scientific advisor of Igor Krichever. It's about 80s, I think. The statement is the following: that u of x, y, and t, moreover, rational function on x is a solution of KP equation, and there is all commuting flows of this, which commute with these flows, which is called the KP hierarchy. So I will write hierarchy, but we will discuss only the first equation in this hierarchy. If and only if u has the form minus 2, just a moment, minus 2, here is the sum of 1 over x minus xi of y and t square. So and this is the finite sum. So it's a rational function on x, but the form of this equation, so the fact that we have here the Schrödinger equation on the variable x, means that it, so if it's rational on x, it should have the poles of second order. It is prescribed by the form of this differential equation. If u has such a form and the dynamics of xi on y coincide sides with the Calogero-Moser system, and the dynamics of xy, it's better to write xy with respect to y coincide with the Calogero-Moser system and its dynamics with respect to t is defined by high flows of the so this definition is a little bit out of our program, but there is a description of this dynamics with respect to variable t. So we will stress our attention with this fact. So if this solution with function is a solution of the KP hierarchy, when the dynamics of poles is a solution of the Calogero-Moser system. But you see they're absolutely different. So KP equation describes some fluid dynamics or plasma dynamics. And as usual, one is interested in describing some special spaces of solutions of this equation. So there are solitonic solution, there are solution of this type. So as you understand, the nonlinear equation is not. So the space of solutions of nonlinear equation is not a linear space. So we are interested in different classes of solutions, and this theorem describes one of these classes. Okay. So we will discuss a part of this theorem. So principally this theorem goes through this linear problem. So one studies solution of this linear problem, some function psi, which solves such equations. And if the space of such function psi is quite big, then this connection is flat. And so the compatibility condition of this differential operator produces a solution of the KP equation. This logic is clear. Is this logic clear? Now I will proceed just to study this equation, and it will define us the dynamics of poles of this function psi and of the function u on variable y. Okay. So I demonstrate a step in this theorem, which is the lemma that dy minus L1 psi L1 if L1 is you remember that L1 is d over dx plus u, and u is of this form. If and only if psi has the form plus sum ai of y and t. So dependence on t is not important here. X minus 1 y and t exponential of some lambda t. I'm sorry, lambda x plus lambda square y. That's plus lambda t. And x I and the dependence of xi on y is a solution of Calogero-Moser system. Okay, so this asymptotic part of this expression is related with the principal part of this differential equation. So here we have d over dy minus d2 over dx2 plus something psi. Here we have dy minus dt d third dx third plus something. So the asymptotic properties at the infinity are prescribed by the principal part of these differential equations. Now, so if we suppose that, so we are studying rational solutions of the KP hierarchy on X, and it says definitely that it has poles of the second order with such a coefficient. So it's just it is just because of this second order derivation on X. Okay, so the analytic form of these equations of this function, the ansatz for the function psi and for the function u, are prescribed by the differential equation. Now I'd like to make a calculation. So I would like to minus d second over dx2 minus plus 2 sum x minus xi, and I would like to apply this function to psi. Psi is 1 plus ai x minus xi lambda x plus lambda square y. I don't write this this asymptotic term. It plays the role on the in the second equation of our zero curvature condition. Okay, d over dy, the function psi, is the following expression: the lambda square psi plus I have to differentiate this expression with respect to y, and there are coefficients and the position of poles which depend on y. So plus e lambda x plus lambda square y have a sum of ai dot. I will denote this dot as derivation with respect to y. So my time here is y. So it is the time of the Calogero-Moser system. I will compare it with the differentiation of on y. I and plus ai x I dot x minus xi squared. Do you agree? Okay. Now I have to calculate the second derivative with respect to x. Second derivative. So it is lambda square psi when I differentiate twice this part, now I have to differentiate one time this part and one time this part. So it is 2 lambda. 2 lambda and the sum of ai x minus xi square, and that's all, and minus. And plus, so now I have to differentiate twice this expression, and it will be the sum of ai x minus xi like this, x and also 2. Here we have also exponential plus y and the same exponential here, and we have also this expression. I will write it here just for the transparency of calculations. Okay, so we have subtract this from this. So here we have to write minus. So it will erase the principal term, and then I have to calculate the coefficient. So the sum is I have to divide by the exponential part. So and the rest is a rational function on x. So I have to calculate all terms of all order at all poles. Okay, the highest term is of order 3. So at the point x, I have xi. I have the expression of such type. Okay. So we have such a coefficient here, and as a product of 2 such terms. But here it is minus ai to ai. Okay. And here we have the same, plus 2ai. So to collect the pole of order 3, we have to multiply so I multiply the summand with the same index. Agree? Do you agree? Okay, so this is 0. Then a coefficient at the pole of order 2. What we have a pole of order 2 here, which is a I x I dot. We have the pole of order here, of order 2 here, which is plus 2 lambda ai, and the half coefficient of order 2 here of 2 types. Let us see. Plus. So the coefficient at x minus xj power 2 is 2 plus sum over j not equal to I to 2aj, and here we have to place xi minus xj. But it is not the end. Please say if you agree. No, it's the end. It's the end. Okay. And we have a coefficient of order 1 over x minus xi. So in this expansion, at the point xi, we have some coefficient at 1 over x minus xi. We have a coefficient here, this ai dot. Here we have not. So we have the second order poles without lower expansion terms. Understand? But here we have coefficients of order 1. So, for example, if you consider this part, we have to take summand here at different points. Okay, I will write, but it is wishful that you follow the calculation. Okay, so I choose this pole of order 1, and in this summation I take all j which are not the same as I, so it is 2, the sum of j not equal to I, and here 2 ai, I fix this ai, 1 over x I minus xj square. But here it's not the end, so we have to expand this second order term. So we have something like this expression. The expansion of this type is the following: x minus over x2 with some function depending on x. So this is a function depending on x. So it is f1 over x2 plus f0x plus etc. Okay, so we have to calculate the value of the derivative of this expression at the point xi. I will write it and please verify. So it's the minus sum over j not equal I 2, but here there is aj over x minus x xi minus xj square. So this is the term which is the derivation of this expression except j equal I. So for j not equal to I, just the derivation, and we place here the position xi. Okay? So this should be else 0. Do you see the Lux representation for the Calogero-Moser system here? Not yet? So this is a trivial condition, but two such equations are equation on a vector function ai. I will write it in the more convenient form. Why it is 0? We have to verify this equation. So we wish that this is the solution of this equation. So all the coefficients should be 0. So what is written here? So all of this I will consider as an equation on variables ai. So here, for example, we have just a linear equation on ai. Here is 2. So it is written the following form: lambda identity matrix here, dt plus dt. I'm sorry. No. Plus L, which was in the description of this part and this part, is 2L in the description of the Calogero-Moser system. And it is multiplied by A plus just the vector 2 is equal to 0. Here A is a vector A1, AN. And all the set of such equation is this matrix equation on a vector A. Just a moment, I have just one problem. This condition, this coefficient is not 2. Okay, it's a little bit different from my definition, but I hope that it is the only question of the scale of the time variable in the Calogero-Moser system. So if I divide all of this by 2, it is I would like to divide all of this by 2. Just L, and L here is such a matrix. It is x I dot over 2, x1 dot x n dot over 2, and the off-diagonal terms are like this. So the difference with my definition of the Lax representation of the Calogero-Moser system is in this factor 2, but let us change the scale of the time y. Okay, and let us describe the second equation. It contains the derivative with respect to our time, so I will write it like this: derivative with respect to y. But here is just our m operator plus 2m applied to a is equal to 0. Just a comment f dy plus m plus 2m and lambda e plus l is equal 0, then it exists a solution of 3 and 4. So let us start by this linear equation. Principally, at a generic point of lambda, it has a unique solution. Okay, because at the generic point of lambda, this is an invertible matrix. This is some vector, so we have a solution of this, a unique solution of this linear system of equations. It could depend on lambda, but principally at a generic point of lambda, it is invertible. Okay, so let A be a solution of free at a generic point of lambda. So we continue it analytically. So it may be some function with singularities on lambda, but it is not important. Okay, and then we apply this equation to this vector A, dy plus 2m applied to A. Just a moment. Be a solution of 3, but maybe we have to fix phi at lambda equals 0. So without this part. It is more delicate, but I would like to say that for generic point of our phase space, it should be invertible matrix. So let us skip this formal question. Suppose that we have a solution, and then we apply this this differential equation to A. So it's some vector, and we can calculate lambda E plus L applied to this vector, and it is the same. No, we will see. So if they compute, it is the same as dy plus 2m lambda E minus plus L applied to A. So I'd like to use that this is 0, not 0, but minus this vector dy plus 2m minus 1. But now let us observe where our matrix M. So that matrix M applied to this vector is 0, and its derivative with respect to y is also 0. So this is 0. Okay, so we have that this is 0, and it means that for a generic lambda, this is also 0. So let us fix the initial definition. So we find solution of 3 at generic point lambda. So if so, then this vector is 0, because at this generic point, this is an invertible operator. Okay, so my mistake was here. So I suppose that all the dependence on the variable lambda is here, but it is not. Is it not true? So this should also depend on lambda, and then it will complete the proof. So, but principally, here the moral is the following: that if we have a large family of solution, the existence of large family of solutions of this system of linear equation is equivalent to this compatibility condition. It is very similar to the compatibility condition in the KP equation, but so it is different form. Okay, so if this is true, then A is the solution of this system of equation, and it means that there exists a function psi of such type which solves this linear problem. And to proceed to the Krichever theorem, we should consider the next equation, which is with the dependence on t, and describe the dependence of poles of this expression with respect to t. But do you already understand how it's related with the Calogero-Moser system? So if we just expand this, we get dy of L. Dy of L, it is a commutator of this. The commutator of this is 0, and the commutator of this operator is 0 because it's a unity operator. So it is just plus 2 m L equal 0. And with my mistake of the scale of the variable, it is just the Lax representation of the Calogero-Moser system. So this is 5. 5 is equivalent to 6. Which is approximately the Lax representation of the Calogero-Moser system. And we get the following statement, that if the poles depend on the variable y as the position of particles of the Calogero-Moser system, when we have a solution of this linear problem. So it's a step to demonstrate the Krichever theorem. Okay. And the next step is about the second equation in the zero curvature condition, which is equivalent to the KP equation. Okay? So we finished this part, and I plan to talk to you about the KdV equation. So we will start, but it's quite a rich subject. So first of all, it has the following form. I will write it like this: ux plus uxxx, maybe plus, maybe minus, but a minus. So now it's a function on two variables. Is a function on variables x and t. And if you remember, this expression is a part of the equation of the KP equation. It is similar to the part of the KP equation, and it is not accidental. So KdV is some reduction of the KP hierarchy, and it appeared in 19th century. Am I right? So no. In 19th century, people found solitons in fluid. So no, it's a 19th century. It's a 20th century. 20th century notion, but the importance of this equation was related with the fluid dynamics, with soliton in fluids. So this equation is manifested to describe the waves in the shallow water channel. So its applicability. It's a very complicated story, but one of the points that this equation has soliton solutions, and we see solitons in fluids, in shallow water channels, for example. And this equation is integrable in very many senses. First of all, it has Lax representation. Lax representation. It has infinite family of symmetries. It means that there is a whole hierarchy of flows on the space of functions which commute with this flow. So this equation we interpret as the dynamic on T on the space of functions on X. So the space now is an infinite dimensional space. And this is the dynamic of a function u depending on X, and which changes, so which become a function on T. Okay? So infinite family of symmetries means that there is an infinite number of times and equation of the similar nature which commute with this flow. So just you have always the zero curvature equation if you start to differentiate in two different directions in two different times in this hierarchy of symmetries. It has Hamiltonian description. And even bi-Hamiltonian description. And all these symmetries, so it means all these flows which commute with the initial flow are Hamiltonian vector fields, and the Hamiltonians commute with respect to Poisson structure described on this space. But all these terms have to be precise. You see now this space is the space of functions, and what is a Hamiltonian? It's some functional on the space of functions. Okay? So for example, so u of x is now a function, some function on x, and it evolves in some manner if we turn on the time t, and we have to treat some functionals on the space of functions. I don't know, for example, an integral of x dx over all the x's. So this is the functional f depending on u. One of the Hamiltonian structures is written in the following way. So the Poisson bracket of two functionals, f and g, as, what is it? It's a differential of df of du prime dg over du these are now functions, and they differentiated over the real axis. So in this subject, we have to change our understanding of what happens. So you understand principally the variational derivatives. What is df over 1?
It depends on the path.
No, it is r. Sorry? Yes, but what is?
The functional derivative.
Yes, it is 1. Yes, the constant function 1. But there are other functions. But this is an integral of an integral. It is an integral of the KdV equation. The second integral is this function. But there are many very important questions on how to work with these functions and functional rigorously. So we have to consider functions which fastly decreasing function, быстро убывающие. Non-exponentially. So we have to consider function which decreasing, which decrease fastly at infinity. Okay. Only in this notation, many things are well defined. So this is not a correct function, but if you work with this function, its variational derivative is also a good function. Okay, so just to give you some ideas how it works, and it has Seletonic solution. Seletonic solution. So it means that you can obtain you know principally what is the Seletonic solution. So it means that you have some localized just solitary waves, but if you have some number of such waves, they interact in a very simple manner. So after interaction, they preserve their form. They could change phases, and this is an interesting phenomenon, but their form is unchanged after interaction. So it was observed on the shallow water, and this equation has solitary Seletonic solution with all numbers of solitary waves. Okay, and it can be treated algebraically. I'd like to give you some initial portion of structures, algebraic structure behind this equation, and it is related with the technique of pseudo differential operators. We have the differential operator d, which is d over dx. And let us just formally consider its inverse operator. So acting on on functions it is not invertible. But we can consider just the algebra of all differential operators on variable x, and to consider its localization. So just to consider this formal sign, and we have to understand how to multiply this operator with other operators, with other differential operators. So we know that, for example, d minus 1 is 1. But now we have to understand how to transpose this differential operator with the function u. This is the question. But you know how to transpose just the standard differential operator and the function u. So it is, if you consider u as a differential operator, as an operator which multiply the function by u. So it is u prime plus u d. So this is the commutation relation between an operator d and an operator of multiplication by u. And here is an operator of multiplication by u prime. How to calculate this? So minus u, I'd like to write it just as a sum of u k d minus k from 1 to infinity. And if we do this, if we suppose such a form, then applying d on the left, we get what we get. We get that u is equal to the sum of d uk d minus k from 1 to infinity. Maybe minus k. Better minus k. K minus k. No, k. Okay. And now we have to apply this commutation relation, and we will get what we get. We get that it is the sum from 1 to infinity u k prime d minus k plus this term k from 1 to infinity uk d minus k plus 1. I will rewrite this. D applied to d minus 1 of u, it is the sum of k from 1 to infinity u k prime d minus k plus sum of from k from 1 to infinity uk d minus k plus 1. Okay? And we would like this to be u, just u. So my statement is the following, that it is true if this is equal to u d minus 1 minus u prime d minus 2 plus u 2 prime d minus 3 minus u prime d minus 4, etc. So you see, if we change here the index of summation, we will get such an expression. So here for k equal 1, I will get just u, and then all terms will cancel each other. Okay? So if we suppose such rules for commutation of the inverse operator with functions, we will get some consistent algebraic frame in which we can make calculations. So our initial operator is d square plus u. And first statement, lemma. One could define a square root of L in pseudo-differential operator. So by this commutation relation, I defined an algebra of pseudo-differential operators on variable x. Okay. So now L, for me, it's a differential operator on x. We interpret the KdV equation now as a dynamic on the space of differential equations, differential operators on operators of type L. Okay. So one could define a square root of L. I will denote it by L1/2, and it will be d plus all some terms. I don't know, b0 plus b1 d minus 1 plus b2 d minus 2, etc. What to do to define this root, this square root? Let us try to multiply to find the square of this expression. So this d plus b0 plus maybe even this term is not important. Just like this. We will see. We will see. It is because there is no linear term here, so we don't need the constant term here. Plus, etc. If we multiply it by this b1 d minus 1. b2 d minus 2, etc. So we get some system of equations. It is d square plus d multiplied by this term, d b1 d minus 1 plus b1 d minus 1 d. Okay. D, and plus terms of smaller order, plus terms of order less than minus 1, less or equal to minus 1, less than 0. And this is what is here. This is b1 prime, b1 prime plus b1 plus plus 2b1, yes, like this, plus 2b1 d, just a moment. It is 2b1 and this coefficients cancel each other, and plus b1 prime d minus 1. So then we make when we use the commutation relations here, we get b1 prime d minus 1. So this is also the term of order less than. So you see the coefficient b1 is defined uniquely. And my statement is that all other coefficients will be defined uniquely if you're solving such a problem of finding the square root of a differential operator of such type. So lemma, one could define a square root. It means that as a series in this algebra of pseudo differential operator, it exists. It is defined uniquely. Okay.
So is this true for any operator?
Sorry?
Is this true for any operator, not only L?
So it's important. It's monic form here. You see. I'm not sure that it is true for. And here, so we have to place here minus. It will be another root. So I'd like could define the square root in such a form. Okay. In the form. It's important. Thank you.
But is this true that for any operator you could do such a operation that to find the square root?
Maybe not uniquely, but yes. It's a triangular system of equation. You can always go order by order. So it's a very useful algebraic stuff. But I will state you some theorem. So I propose to make a break, but to spend some time from the exercise part, just continuing calculations.